All right. Good morning, Andreas. There's a great inspiration for this project I'm going to talk about. So 6 years ago, I started to work on quantum computing, and I want to understand the fundamentals. And what more inspiration can one get from this than following in your footsteps? I want to talk about optimal quantum programs, and really, we have a whole community now working on optimizers, compilers, tools for quantum computing. And the tools are getting better and better, and they will definitely help usher in the quantum revolution. The question is, my question is, how close are they actually to getting anything optimal, and what does optimal even mean? And so what I want to talk about today is really that I want to persuade you that really one can sometimes get optimal programs, and one can on a good day prove that they are optimal. And so I was really diving into a fundamental question like we have seen Andreas do so many times. And so I'm going to go over 3 points. I will talk about some concepts of reliability that people use in quantum computing. Then I'll show you a couple of optimal programs, and then I will present a technique for proving that programs are optimal. And so that's where I'm headed. This is a quantum circuit. So I just want to sort of introduce the notation a little bit. This is we kind of got this from physics. They like to draw things that look like a circuit diagram. There are 3 qubits. They're called A, B, and C. Each qubit gets its own line. And then each of these thingies here is a gate. And so you can just think of it as a gate as we're used to in classical computing, except that it's gates in quantum computing. And you can see that sometimes a gate operates on 2 qubits, and sometimes it operates on a single qubit. And then the notation is sort of supposed to say what kind of gate we are talking about. And in quantum computing, it's applied linear algebra. So everything you see is linear algebra. So really, when you have 3 qubits, you have a vector of 2 to the 3 complex numbers. And when you have, say, a gate like this that works on a qubit, well, that's got to be a 2 by 2 matrix. And then a gate that works on 2 qubits, it's a 4 by 4 matrix. And that's really all it is. So it's just like all linear algebra all the way. And so the time kind of goes from left to right as usual. And then the idea is that once you've executed all these things, you get a final state, and that's the result of your computation as usual. And as you can see, it's very finite. That's how it always is. So it's only the Popple people and the PLDI people who talk about infinite quantum programs. In physics, everything is finite. Maybe it has to do with that we know that quantum computing sort of tends to be up against the idea of decoherence. And so at that point, it's like finiteness kicks in. That's where quantumness falls apart. But for what it's worth, quantum computers today are very unreliable. If we look at a gate like these single qubit gates, on a good day, on the best quantum computers we have today, reliability is maybe 99.99%, which sounds like a lot of nines, but it's, of course, if we compare with this laptop here, there's probably 1 error per year. So executing one operation with 99.99% is not that good. And these 2 qubit gates, it tends to be more like 10 times worse, 99.9%, just for executing a single operation. And so, so the first concept of reliability that people use is plainly to multiply up the reliabilities of these gates. And so you can see you don't have to multiply very many of these before reliability drops below 50% or 1% or something. And so that's why current quantum computers, they're neither big enough nor reliable enough to do anything useful. And I think we are like a decade or 2 away from that happening. But of course, we can still have fun studying the fundamentals until then. And also there's another thing. If our goal is to produce optimal programs, then working with an objective function that is the product of a bunch of reliabilities, that's a miserable objective function because it's highly nonlinear. And so people don't do that. So it's great to think about. This is really the sort of the ultimate objective function we should think about, but that's not what people study in practice for their tools. And so I'm going to go to another little bit friendlier notion of optimality, which is not the most reliable circuits, but instead the circuit that has the shortest, or the people would say the lowest depth. And so by depth, they simply mean how far is it from left to right, counting in number of gates. And of course, if the depth is small, that would tend to mean there are fewer gates, which means that the reliability product is smaller. So it's a good idea to try to decrease the depth. And overall, clearly, a shorter program should mean faster execution time. So this should be a very good idea to study this. And so if we think about how we would go about getting us a smaller program, I just want to give a quick idea of what is it we are doing when we are compiling quantum programs. And so really, I know that there are many good papers in PLEI and in POPL and so on higher levels of abstractions. But when it comes down to what the people in physics are studying, there are really only two abstractions. The first abstraction is that we don't have to use the gates that are supported by the quantum computer. We can use any kind of, really they're unitary matrices, any kind of unitary linear function we can use. And then what this translation step is supposed to do then is to compile to the gates that are supported by the quantum computer we want to run on. The second abstraction is that really when we look at the quantum computers today, many of them have restrictions on which gates, in particular 2-qubit gates, what they can do. And so if we just look one step back here, then you notice that I have gates here that operate like a 2-qubit gate operates on B and C, A and C. Over there's one A and B. Nobody says that the quantum computer supports all of that stuff. So that's the second abstraction, that we can just do whatever we want at the source level, but at the target level, we have to follow whatever is actually implemented there. Maybe there are only connections between A and B and C. So then we are back to the mapping step. That's what the mapping step is doing. So it's like insert some swaps is a typical thing that these compilers do, that will then swap things around following what's implemented, and then we can do our work. So that's how it goes. So then we can say, okay, fine. So inserting swaps, that's inserting more gates into the circuit. That's going to increase the depth. And so it means that if we're going to try to do all this stuff, including solving the mapping problem, including inserting swaps, that's actually NP complete to get a minimal depth circuit. That's not so difficult to see. NP completeness, that means the compilers that we are using for quantum computers, actually, as many other compilers do, I guess, in classical computing, they are solving an NP complete problem somewhere along the way. And I want to say something about how hard a time people are having with that problem. So the reliability criterion, I already said, people are not even working on this. This one here, minimal depth, people are working on a lot. There are lots of tools. And it's not going too well. So I just want to go with a paper from my floor at UCLA, which I'm very fond of. So what they did was that they set up hard challenge problems. And then they say, okay, let's just run people's tools, people's compilers, and let's see how they do. And so what they do is a trick that was known from the CAD community from decades back. The way you challenge any tool that solves an NP-complete problem is that you make a really hard instance, and then you obfuscate it. And so in their case, what they do is they say, let's say we have this quantum computer over here. It supports 5 qubits, and these blue lines are the connections that sort of sets up which 2-qubit gates are actually supported. The other ones that don't have blue between them, you cannot just directly do what you would do at the high level. Now you have to swap around to make things happen. Then the second thing they do is they set up sort of like the core of the challenge problem over here. And that's just plainly a circuit. And there are these sort of free layers here just to sort of say, here's what we do at time 1, here's what we do at time 2, here's what we do at time 3. And that, it doesn't have to be an optimal program itself, but at least it's set up so it looks like very, very hard to do anything about that program. And then they obfuscate it. And so just to do a little bit more here, now they just sprinkle in gates just to make it hard to understand what's going on. And they're following all the rules of the quantum computer in front of them. This is like programming at the low level. And then what they do is they scramble everything. So this is the scrambling phase over here. They say, we were following the rules, but nobody says that we call our qubits exactly what they were called on the quantum computer. We'll just scramble it around. So of course, what is that? There's a whole bunch of different scramblings you can do, right? There's math that sorts this out. And so at that point, what you get is, in this case, there's the circuit. Give that circuit to whoever people's tool, a compiler we have in front of us, and let's see how well it does. So this paper here was published in 2020, so I think we should redo all their experiments. But what they did at the time was that they picked some quantum computers that have something on the order between 16, 54, 20 qubits. And then they created these challenge problems. They followed exactly the recipe that I showed. And what they then discover is when they tried the Qiskit compiler from IBM, the Cirq compiler from Google, and what they discover is that the depth that come out is way higher than the optimal program. So of course they know how good it can get because that's where they started before scrambling. And what they find is that it's like 10x worse. So enormous numbers of swaps got inserted. And the state of the art has not gotten a lot better the last 4 years. People are still working on it, but another way of saying this is that if we really want to get to a sort of a mathematical understanding of what's going on, this criterion is too hard as well. So then we can say, okay, so maybe this thing with the depth is too hard. Maybe we should just go to number of gates. And in particular, as I said, the 2-qubit gates are 10 times on current quantum computers. They're 10 times more unreliable than the 1-qubit gates. So it would make sense to focus on minimizing the number of 2-qubit gates. And there are lots of optimizers out there. I sort of listed sort of my favorite ones here. There are more, and we can sort of just plug them in and just again take some circuits. It doesn't have to be these hard challenge circuits. It could be anything, and just see what happens when you optimize. And so I would say my experience is that sort of on a good day you can get maybe 30%, maybe a little less, maybe a little more. If it's a very hard circuit, maybe you'll get a lot less. But if you think of as 30%, then I think that's pretty good. And so now it's like, okay, 2-qubit gates in particular, let's focus on those. Can we get optimal circuits this way? So I'm not going to discuss whether these tools give something optimal, but what I will do now is to simply jump to something that I know is optimal. And so that's my second point. So I'm going to focus on this fellow here. It's a famous gate. That's the Toffoli gate. It's a kind of a conditional gate. It's like an if-then-else with two conditions. So the A and B qubits, that's like the condition qubits. And then C is the target qubit. And what this thing is saying is if qubit A is 1 and qubit B is 1, then we do something to qubit C. And in this case, it applies an X gate, which is one of these gates again. And so it's like, okay. So most quantum computers don't support anything that operates on 3 qubits. So there has to be a translation phase that we map this to gates that's supported by the quantum computer. And what could that look like? And so I'll go through a couple of sort of translation steps, just with in mind that I'm going for the minimal number of 2-qubit gates. And so it turns out that if you draw this 3-qubit gates on 8x8 matrix, it's not diagonal. But of course, we know we can diagonalize stuff. And in this case, the diagonalization looks like this. This is a different 3-qubit gate sitting in the middle here. And it's a diagonal gate. And then all we need to do is to diagonalize by conjugating by something on each side, 1-qubit gates there. So no 2-qubit gates were introduced to do this. So our Toffoli gate is actually equal to this thing over here. This could all be written out in math, but I thought this is a birthday talk, so we'll just draw pictures. And indeed, this thing here can be written, the notation people like is sort of control C. And it's very much a diagonal matrix. So there it is. It's like, okay. So this means that now we can focus on seeing what's the smallest number of 2-qubit gates to implement this diagonal matrix here. This is like this is a topic that has been studied for a long time. I think the thing I'm going to show next, I think, was actually known to Feynman all the way back into the 80s. And people keep studying variations of this problem here. So this is the thing that I believe Feynman knew, which is, that's actually the circuit that I showed earlier. This thing here, if you start counting, is saying, see, here's it 1, 2, 3, 4, 5, 6 2-qubit gates, and then some 1-qubit gates as well. This is an implementation of CCZ, and in 2008, Shandy and Markov proved that this is actually optimal. If all you have is these CX gates, or C0 gates, as some people call them, as 2-qubit gates, then you cannot do better than 6. And so that's an optimal one. So you can see it took people quite a few years from the 80s to 2008 to prove that this is optimal, and this is absolutely not an easy proof. But instead of focusing on this one, I want to focus on another one. So here you're imagining a quantum computer that supports CNOT. So that would be like an IBM quantum computer. That's what they tend to do. But there are many other quantum computers, and they will support other 2-qubit gates in particular. And so to be able to talk about this in general, let's look at just using any 2-qubit gates. Doesn't even have to, just any unrestricted, whatever 2-qubit gates you like. And it turns out that now we can do it with 5. I don't even need 1-qubit gates here. You can see it's very clear. 1, 2, 3, 4, 5 2-qubit gates here. And so they do whatever they do. You can see they all have this structure of there's a control, there's a target. It's conditional gates, all of them. And in 2013, Yu, Duan, and Ying proved that this is optimal. This had been an open problem for, at least it appeared in the famous Nielsen and Twang book in 2000, whether this is optimal, and they eventually proved it. And as it happened, Ning-Kung Yu came out to visit me just before Popple in 2020. And so we talked about computer science, and he said, I somehow mentioned this paper. And so I have this thing that I'm teaching a sequence of 2 quantum courses at UCLA. It's like Quantum 1 and Quantum 2. It's like the survivors go to Quantum 2, but I've had something like 500 students come through Quantum 1 already. And I was in the middle of preparing for this Quantum 2. And I was thinking, oh, this is a wonderful paper. It's like 4.5 pages. And you know, a lot of it is text and references. The proof is 2 pages. So I thought, this is wonderful. It was a Sunday morning. I'm going to read this over Sunday, and then I'll teach this on Tuesday, right? Okay, 2 years and about more than 100 one-hour Zoom calls later with this Ning-Kung Yu, I finally understood the proof. And it's written up in LaTeX. In my version, it's 60 pages of proof. And I am going to say something about how this works. As an aside, I tend to give homeworks in my classes. And one of those homeworks is to see, well, maybe even if 5 is technically optimal, maybe you can get close. So I give a standard homework that is just you only get 4 2-qubit gates. Just get as close as you can. And this is actually the best anyone has ever come up with. There are many, many variations of this, but they all come up with the same distance. There's a distance measure on matrices that I really like called the Hilbert-Schmidt distance. And this one has the best Hilbert-Schmidt distance to toffoli one can get, and it's not close. It's 0.38268, and if you want a formula with square roots of 2 in it, I can give you that as well, but it's not close. So nobody would use this as an approximation for toffoli. It's too far away. And so, I just want to understand, why is this one then optimal? And I have really sort of done the Andreas thing of diving into the fundamentals of this. And I just want to give you a sense of how it works. So it turns out that there was a generalization of this thing that we need 5 2-qubit gates to implement toffoli. That was 2 years later by some of the same authors. And so this one here says, I'm going to sort of like read this out loud. It says something general that then implies what I said before. So the idea is that we want to show that you cannot get very far with the product of 4 matrices, a sort of a circuit of 4 2-qubit gates. And this is now formalized. So it says if we have a product of at most 4 2-qubit unitaries, that's equal to, now we are going to generalize to control anything here. It doesn't have to be X or Z or anything else, but anything at all. Then this happens if and only if that one qubit gate that's sitting here, either the eigenvalues of that thing are equal or the determinant is 1. And then you can immediately see that if we are doing control set, then if you just sort of look at the details of what that matrix is, that's a diagonal matrix of 1 and -1. Then clearly the eigenvalues of that are 1 and -1, so they are not equal. And the determinant's got to be 1 times -1, that's -1, so it's not 1. So it means that this theorem immediately implies that we cannot implement control set in 5 gates, in 5 2-qubit gates, and similarly for control X. Okay, so how are we going to prove this? That is my question here. So here's a diagram of my proof. So this just appeared in linear algebra and its applications. It's the first math paper I ever had, and have in a way, in the sense that it was published in a math journal. And so the proof goes as follows. I'm going to like hand wave my way through how to go about this. So in the actual paper, I have 50 theorems or lemmas that sort of spell this out. This is the highlight of that. The first point is we are starting with this general CCU. The first thing we do is we diagonalize, like I did before. So that gets us to theorem 7.4. Theorem 7.4 is the gigantic case analysis that takes all these different products one could think of for implementing just products of 4 things, products of 4 2-qubit unitaries, and breaks it down into, thank God, there are only 2 cases that captures everything. And those 2 cases are then 5.1 and 6.4. It's like there's a reduction that just reduces that to the general case. Now we can look at each of those 2. And so in a way, they are very similar in proof, except that this one is like 10 times more of it. So I'm just going to talk about this one over here. So what we do in lemma 5.1 is we say, okay, so we look at this particular case of a product of 4 unitaries. We don't really know what they are, but it's a case in the sense that the first one, say, works on A and B, and the second one works on B and C. And it's like it's restricted in that way. And then we stare at it, and then we discover that it's almost like program analysis, if we take this product as a little program. We discover that actually, if that's equal to CCU, there's no way that these 4 matrices could be general. We sort of start to discover that they have properties, and in particular, we start to discover that they are conditionals, some of them. And then it's like, oh, so if we know they are conditionals, then we can go back and say, what did we learn? And then we can like do the product again, but now knowing that some of them are more special cases. And it turns out that that's where once we have discovered some things, we can plug in lemma 4.1, and lemma 4.1 then says, oh, and then you get the result from the previous page for that case. In some sense, we could stop here, but there's still this question of where did this idea that the eigenvalues are equal or the determinant is 1, where did that condition come from? And it turns out that it comes from lemma 3.2 in this case here. So I'm just going to state lemma 3.2, and then you can get a sense of that this condition down here, it's still there. There are 2 things that are equal. That's like the eigenvalues, or the product of them is 1, so that's like because it's a diagonal matrix that it came from. It's like that the determinant is 1. And there's a much simpler property that we can now look at. So this gives me a chance to talk about tensor product. So in quantum computing, when you have 2 unitaries that work on 2 different qubits, the way we can sort of model this mathematically is to talk about tensor products. And so I guess today it's like there's no need to understand the details of this, but it is a way of combining 2 matrices, in this case 2 by 2 matrices, into a 4 by 4 matrix. And it turns out that if the eigenvalues of that is 1, 1, U0, U1, so that's something that comes up all the time, if it is the case that you can find such 2 unitaries here, then this is only going to happen if U0 and U1 satisfy these properties here. And so when you sort of dig down, way down under this property of can we implement TOEFL with how many 2-qubit gates, this is the lemma that we really, really need, and then everything just builds up on top of that. So we formalized almost all of this in Coq. The Coq proof is like 16,000 lines of Coq. What we did was that we started with Robert Rand's library, who had been working on formalizing quantum in Coq way before we started. And he has actually helped us along the way. There was a point in February where I had to ask Robert for help. And so we had a bunch of trouble with the spectral theorem, but he solved it all. And we are down to 1 lemma, not even one of the 50 lemmas I mentioned, but a support lemma that's like obviously true if you ask a mathematician, but Coq just has trouble with that lemma. So we are working on that 1 lemma. So we're 1 lemma away from formalizing all of this in Coq. And then, as you can see, this is all linear algebra. It's just formalizing a lot of linear algebra in Coq. So it's very natural to start to talk to the mathematicians about this. So, for example, the other day I had lunch with Lin from Berkeley, and it was just like talking about formalizing stuff in math. I also talked to Terence Tao at UCLA, who's one building away from me, and he said, "Oh, I like Lean much better than Coq." And it's like, what's your reason for liking Lean much better than Coq? He said, well, it's such a nice math community. We all help each other, and it's like we have this wonderful library that we build on. And so I have started to think about, does that mean that we should just move to lean? So I feel really bad because I'm like heavily invested in the sort of POPL PLDI community, but I think the time may come. So I found 5 students at UCLA. Some of those know both COG and lean, thank God. And so we are going to start to work on it this fall. And so if there's any one of you who knows anything about how to go from COG to lean, experience, prejudices, biases, whatever you may have, I would like to know about it so that we don't ruin our fall completely here. But that's where we are going. So Andreas, congratulations. It's like that. This was a 2-year journey for me just to understand this proof. And this is like where we need inspiration from people like you to just stay with it and really try to say, I want to understand the foundations and the fundamentals. So happy birthday.
Thank you.
Will you ever run one of these programs on a computer yourself?
Yes, of course. Of course.
Have you?
Yes, of course.
Really?
But we run it, say, an IBM. So you mean the quantum part, not the COG part?
Yeah. How do you get access?
There's online access. So sometimes it's online. Okay, so I have like a little story. So in the beginning, back in 2019-20, I ran into somebody who works at Rigetti, one of the quantum companies, and I said, could we get access for my class? And she says, yeah, we can probably work something out. So we sort of like maneuvered our way in, and we ran on Rigetti the first year. Then the second year, we are very well connected to Google. The guy who was the program manager for the Google Quantum project over in Venice, 4 miles from us, he's married to my closest colleague, Miriam Kim. And so we see him all the time. So it's like, hey, could we get to run on Sycamore, which was their biggest quantum computer at the time. And it's like, yeah, we can probably do something. So in contrast to IBM, which is famous for having this wonderful web interface, very automatic and so on, Google didn't have any. So we actually built the interface to run on Google's quantum computer. And then we got Colorado School of Mines in there. And then after we were done, they discontinued the whole thing and said, well, that was the experience with academics. We're not doing this again. So I don't know whether we ruined it for everybody. Now, after that, they only support researchers. So they don't want to give their quantum computers for teaching anymore. They only, if for research, I could probably get access to Google. Then we also ran on IBM, and I've sort of forgot the rest now.
Most of the students in your class must be just running on simulators. Or?
They run on simulators for part of the time, but some of the homework insists on that they run on quantum computers.
Okay.
Right? So it's like if you're going to convey excitement in this, you got to have at least one homework that runs on a quantum computer. Then you will see that it works like crap, right? That's a technical term. And then you go back to simulators immediately, right? But you got to get the experience just to get it into your classroom.
Thanks, Jens. And for the optimality part, and also for the foundational aspects of actually taking a problem and studying in fundamentally. So in classic computing, we've studied actually, complexity and figuring out along how much space and time, things are. So the basic model we've used is actually saying like getting access to something that's arbitrarily far away. That's 0, right? That's the random access model. But adding to numbers, boy, that we really count. Yep. So in practice, it means that all the kinds of optimizations we make are completely irrelevant. It's all about distance, right? Yep. So it's all about, and it's the same thing with quantum computing. Yep. So I'm asking, because it's even worse, you could say, because it depends on actually what technology you're using. So I'm asking the following thing: is like, are we on the way now, entering this intense, competitive, fun phase of studying something, optimizing it? That's clear. That's in the end irrelevant. Because we're actually ignoring the complementary and much more important problem of actually layout, low dimensional layout of data and all these things.
So I have an answer, but it's not a layout answer. So Ryan Babush, who runs the quantum algorithms group at Google, came out to visit us a month ago, and he gave sort of all the last papers of the last 2 years, I think, that they had produced of algorithms, and he tends to count either T gates, like I had an example, or Toffoli gates, actually, that I talked about a lot. And so I asked him, why are you counting those things? And he said, because we are looking ahead to that there will be a day when we have error correction on the quantum computers. And at that point, the things that will be really expensive, sort of really, really expensive compared to everything else to execute, will be T-gates, or more or less equivalently Toffoli gates. We can have a discussion about that. And so he said, that's what you should count. And so the last month, I've actually more or less made it a point out of every time I meet somebody in quantum, I say, by the way, do you agree with this? And so far I've gotten yes, 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 100% yes. So I think that the point here is completely correct, that we should know what to count. And I think the day will, actually what Ryan said to me was, I said, I'm counting 2-qubit gates. And he said, oh, this is such a NISQ thing. So NISQ stands for the near-term intermediate scale quantum computing. So it means it's more or less the 2020s, not very large quantum computers. It's not really working that well. And so we are counting 2-qubit gates because they're the most unreliable. But once error correction works, then that point ceases to be as important as what's really hard to implement, and that'll be T-gates. So
but it's still the gates.
It is still the gates and not the distance. So I think that, so this opens up a whole other thing. So now there's a whole different topic that comes in, which is like super unresolved, which is what is actually the future of error correction. And it looks like quantum error correction is due for a revolution the next, I would say, 24 months. I talked to lots of people in the community, and there's this new thing called LDPC codes, low density parity check codes, that is going to revolutionize everything. And they will just dramatically change how many qubits we think we need to support one like source level qubit. So right now the conventional wisdom is 1,000 physical qubits to support a single logical source level qubit. That number is going to drop. And once that number starts to drop, we'll start to get much more realistic about, okay, so what are the resource requirements here and what should we be counting for thinking about optimality? And then I think your point comes back in, that the actual layout of the qubits is going to be key again. Right now there's this gap between that the error correction people are over there and these sort of mapping people are over there, and they don't talk a whole lot.
I think we have time for one more. If not, let's thank Jens again.